Hello, in this video I'm going to go over a problem I did in class last week where we were looking at different cases of equilibrium on an inclined slope, and not all of them were limiting equilibrium, because a common misconception, I think perhaps because so many A-level questions involve using the formula F equals mu r, because it is appropriate a lot of the time, students tend to just latch onto that when it's not appropriate. The general case is that friction is limited, or the kind of frictional element to the contact force is limited by the formula F is less than or equal to mu r, where F is the frictional contact force and R is the normal contact force or reaction force. Okay, so here's the problem. So we've got, first of all, a situation where it's told us mu is equal to 0.5. But as I say, it's important not to fall into the trap here of just saying F is equal to mu r, because it won't be in many of the instances here. And then there's some kind of modelling, because remember, mechanics is all about modelling. So there's different situations where we do a bit of maths, a little bit of resolving, and then we are kind of led to kind of interpret what we found from that. Okay, so let's just maybe use this diagram here to actually do some of our resolving. So let's look at the first part of this question, which basically says that the theta is the unknown here. So basically we can almost regard this as a problem where, what happens in this scenario where we've got a weight of 10 newtons, the mu is equal to 0.5, an external force of 2 newtons, which is parallel to the horizontal or coming into the slope like that. What happens with different scenarios of theta? If theta takes different values, what's the difference between them? And that's what this problem is essentially about. Okay, so the first, let's just do the first. It says by resolving parallel and perpendicular, and we have seen how important it is to do parallel and to be able to resolve parallel and perpendicular to a slope before. We've seen how important that is. And we're going to do that now, and that's going to enable us to get expressions for the normal contact force R and for the frictional contact force F. Okay, so let's just home in on this now. So we're going to do the resolving equations. So let's first of all resolve parallel to the plane. That basically means that all the forces up. We're going to look at forces in this direction. It's gone a bit wavy, that line, isn't it? But we're going to look at forces in this direction, like that. And we'll take, in this instance, it positive, but we sometimes take downwards as positive, but I'm going to take upwards as positive here. The important thing here is that the reaction force doesn't come into our equations because that's perpendicular. So there's no R in our parallel. No R, no normal contact force in our parallel equation. So let's do the equation. I'll change pen color to blue. So resolve parallel. So up the slope we've obviously got the F. That's no need to fuss about that. It's not at an angle. It doesn't need to be resolved in any way. So that's F. And then we've got, let's look at the 10 Newton force. It's going in the opposite, the component is going in the opposite direction to F, so it's minus. And then we have to decide whether it's 10 sine theta or 10 cos theta. Well, because actually we'll get used to, you should hopefully already be used to the component of the weight down the slope being sine. But here's sine because we've got kind of space here, so it's away from our marked angle. So that's 10 sine theta. Okay, so that's the 10 Newton force dealt with. And then if we mark on this angle theta here, then we can resolve parallel to the slope. This is actually going to be positive, that component, isn't it? It's going to be upwards like that. It's going to be upwards like that. And again, it's marked next to the angle that we've got theta there. So that's 2 cos theta is going to be that component. So that's plus 2 cos theta equals to 0. So we want an expression for f. So let's just rearrange that to f equals 10 sine theta minus 2 cos theta equals to 0. Right, okay, so that's the parallel equation done. Let's do the perpendicular equation. Okay, so let's look at perpendicular. I'll keep the angle theta there marked on. So again, this time we'll take this way as positive, and this time the frictional force is not going in, it's going perpendicularly to that, so that's not going to come into our equations, and the R, the 2 and the 10 Newton forces are going to come into our equations. We'll take upwards as positive, so no need to fuss about the R, doesn't need to be resolved. Then we can do the component of the 10 Newton force, which kind of goes into the plane like this. Now we've marked the angle theta here, so that will be, the component is next to it, and again you should be used to seeing the component which is perpendicular to the plane for the weight as 10 cos theta. So, and again we just need to check the sign. Well, this way is positive, so this way is going negative, so that's minus 10 cos theta. Now let's turn to the 2 Newton force. That's going into the plane like this. And again, this time it will be in the opposite sign because it's going in that direction, which is negative. So that's minus 2. Then we've got to decide whether it's sine or cos. Well, we've got, again, this space here. The angle we've marked here is theta. So that's 2 sine theta equals to 0. So that's R equals 10 cos theta plus 2 sine theta. So that's our first part done. Okay, so that's going to help us with part B. It says find the value of theta where there is no frictional force. Well, it's a rough slope. So under what circumstances would it be where there's no frictional force? Well, we can talk about what's going on with the physics and mechanics with it, and that's actually going to form part of what we're going to talk about later here. But basically, there will exist a value of theta for which the 2 Newton force itself basically is enough to hold the 10 Newton force in place, and friction is not required. But anyway, in terms of the mass, all we have to do is apply F equals to 0 into our equation here. So that gives us 10 sine theta minus 2 cos theta equals to 0. And then that we can change over to 10 sine theta equals 2 cos theta. So that's going to give us sine theta over cos theta equals 2 over 10. So that gives us tan theta equals 1/5. So if it's only asked for the tangent of it, but at that angle, whatever it is, 11.4, it does ask for the angle, doesn't it? It actually asks for the angle, the value of theta. So if we find the inverse tan of that, it's going to come to 11.3. So at 11.3, and this is going to help us in a later question, at 11.3, friction 0. Okay, friction 0 because there's no need for friction because the 2 Newton force is enough to hold up the whatever the mass, the 10 Newton, the particle. Okay, which is of weight 10 newtons. The 2 Newton force is enough to hold it when the angle is 11.3 degrees. Okay, so the next part is where the idea of limiting friction really comes into play. If ever you see an inequality in a statics question, it's going to involve the fact that friction is limiting. There's a limit to what friction can be, and that's the thing that needs us. That's the thing that enables us to get our inequality. So we have our expression for F, which is 10 sine theta minus 2 cos theta. We have our expression for r, which is 10 cos theta plus 2 sine theta. And as we say, friction can't take, so if friction does not satisfy this inequality, then equilibrium is not possible. So friction can't just carry on increasing forever, it's limited by that. So we can just put our expressions in, and we're told that mu is 0.5, so we can just put that into our expression to get tan theta, the inequality that we require. So 10 sine theta, let's make it a bit bigger now, 10 sine theta minus 2 cos theta is less than or equal to 0.5 times r, which is 10 cos theta plus 2 sine theta. Okay, and so that means that we can multiply that out. 10 sine theta, well, that looks like a theta there, doesn't it? So 10 sine theta, still looks like a theta, but never mind, sine theta, minus 2 cos theta is less than or equal to 5 cos theta plus 1 sine theta. So we can take that over to the other side. We get 9 sine theta is less than or equal to 7 cos theta. So divided by cos theta, let's get sine theta over cos theta is less than or equal to 7 over 9. So tan theta is less than or equal to 7 over 9 as required. Okay, so that's a common thing that happens, probably less common, it's getting more common, I think, with modelling, and the syllabus really emphasises the idea of limiting friction. So we need to appreciate that this is the general case for friction. That's what friction, rather than F equals mu r, which is the case where it's moving or on the point of moving. Okay, so that brings us to this kind of scenarios that we're going to look at in the next 4 scenarios from the work we've done, and that will give us a clue as to how to answer those. So now let's look at the 4 scenarios. It's asking us to explain what's happening in these situations under this model. So basically, for different values of theta, different things will happen. So tan theta greater than 7 over 9, well, we've kind of already, the hint is in this question here. It's basically, if it's not greater than 7 over 9, then friction has kind of done the maximum it can. You can't keep it in equilibrium anymore. It can't just go on increasing as we increase the angle of theta. It's going to start sliding down. So it's basically a situation where, you know, you've got this, it's going to accelerate down the slope. So accelerate down slope if tan theta is less than 10 theta is more than 7 over 9, because friction can't hold it anymore. So tan theta is greater than 7 over 9, so accelerate down slope, because the component of the weight down the slope is just can't be held now by the combination of the 2 Newton force and the friction down the slope. So accelerate down slope. Okay, so that's the first bit. So hopefully the next bit is fairly intuitive as well now, because this is like the boundary, if you like, the boundary between, you know, it's on the point of moving down slope, but it's in point of moving down slope. So that if tan theta equals to 7 over 9, so it's in limiting equilibrium. So now let us turn to the final 2. The clue was really in part B, which was where I showed that tan theta was equal to 1/5 and the angle was 11.3, and that's where the distinction between these two are. They're both non-limiting, but the direction of friction changes, because at the point when tan theta equals 1/5, it doesn't need any friction. It would actually stay on the slope just at that point if it was smooth. So if tan theta were greater than that, we would need some friction upwards for it to be in equilibrium. And we know it is rough and there's perfectly enough friction, but we do need friction it would actually go, basically imagine it was smooth. If it were smooth, then between these two values, or not to, well, less, if tan theta were greater than 1/5, it would be moved down the slope, whereas if tan theta were less than 1/5, it would move up the slope. So that determines which direction the friction is. But they're both non-limiting. It's never in this scenario with these numbers, with the 2, the 10, the 2 newtons and the 10 newtons, and the mu equals 0.5, limiting equilibrium never happens where it's on the point of moving up the slope, because the 2 Newton force is just not enough with it being that on this rough surface. The 2 Newton force is not enough. So answering the question then, for part 3, it's non-limiting, and friction is up the slope to stop it from moving down the slope, which is what would happen if it was smooth. And part 4, non-limiting, friction is down the slope. Okay, but it's never limiting the other way. It would actually, theta would have to kind of be negative in that case for it to be on the point of moving down the slope, which then would be on the point of moving up the slope, which then it wouldn't be up a slope, it'd be down. So it's never with this rough surface. Remember, look at the actual numbers, they were kind of chosen deliberately. Obviously it'd be quite different if this force were much more, then we will reach a point where even on a rough surface of 0.5, there would be enough that there would be values of that force which would make it tend to move it up the slope, and there would be a limiting situation where it's on the point of moving up, but not with those numbers that we've got here. Okay, so finally one last bit, although we're back to some more mathsy things here, where we're finding a value of theta which is 45, tan 45 is 1, so we're in scenario 1. It's going to accelerate down the slope, so we're applying F equals ma and all the rest of it to actually determine the acceleration. So let's get on with that. So it's going to be similar to before, except I suppose I might as well take downwards as positive now, because it's going to be accelerating down the slope when it's 45 degrees. My resolving perpendicular equation is going to be very well identical, apart from we're going to put 45 in for our angle. So we got R going up the slope, F doesn't come into it. R goes up the slope. The component of the 2 Newton force, which is going in the opposite direction, so that's minus 2 sine 45. And the component of the 10 Newton force, which is also going in the opposite direction, so that's minus 10 cos 45. We're in a kind of situation now with the 45 degrees where we'd get away with mixing them up, because sine 45 and cos 45 are the same thing. So I can't possibly say you're wrong, but anyway, just for consistency, I've put the same ratios as before. So that's the same equation as we had before, except just theta is 45. Now our resolving parallel equation is going to be similar to before, but now we can say that F equals mu r in this particular situation. I might do that later, but we can say F is equal to 0.5 r in this situation because it's moving. It's moving, it's accelerating actually, but it's moving. So f equals mu r now. As I say, as I've mentioned before, that's why I think so many students just always write f equals mu r even when it's not. So f equals to 0.5 r. Let's do the parallel equation, but I'm going to take downwards as positive. So let's take the only downwards one that does have a component downwards is the 10 Newton force. So that's 10 sine 45. There's no g in that because we were told the weight, not the mass, and I'll come back to that in a moment. We were told the weight of it. So the weight isn't 10g, the weight is 10. Okay, so there's no g in our equation in this particular thing. That was our original diagram. 10 Newton force going downwards. It's not mass 10, it's weight 10. Anyway, so 10 sine 45 going down the slope. So going up the slope, which in this time is negative, that's minus 2 sine 45. So it was cos 45 to be consistent, so it's 2 cos 45 because we're next to the angle there, 2 cos 45. And then also minus 10 sine 45. Where's the f? Something's happened to the f. Oh, I've already put the minus 10, not the minus 10 sine 45, minus the f. I've gone the wrong direction again. So up the slope, we've got this down the slope. So that's positive. And we got this up the slope. And we got this up the slope as well. So those two are negative. Sorry about that. So equals to mass times acceleration. Now, as I've just mentioned, the mass, the weight is 10. W equals mg is our general situation. So W equals mg. So in this case, the mass is equal to 10 over g. It's a bit of an unusual situation where we're given the weight and we want the mass, but there we go. That's what it is. 10 over g is our mass, times by acceleration, which is what we're being asked to find. Okay. We're also told that f is equal to 0.5 r, so we can just put 0.5 of all of these into our equation. So we've got 10 sine 45 minus 2 cos 45 minus 0.5 r, because that's f equals mu r, f equals 0.5 r, so that's 0.5 times by r, which is 2 sine 45 plus 10 cos 45. And that equals to 10 over g times by a, and a is what we're being asked to find. So let's do a bit of simplification of this. 10 sine 45 minus 2 cos 45 times by 0.5, that's minus sine 45 minus 5 cos 45. So that's 11 sine 45. No, not 11. 9 sine 45. Minus 7 cos 45 equals to 10 over g a. Well, sine 45 and cos 45, I'm going to put the exact in. It might be useful to have an exact answer. So they're both the same. They're both the square root of 2 over 2 equals to 10 over GA. So that's 2 the square root of 2. So this, all this comes to, that's 2 the square root of 2 over 2. So that's the square root of 2 equals to 10 GA. So the acceleration is equal to the square root of 2g over 10, meters per second squared. Now, depending on the wording of the question, that's actually quite, in mechanics, often an acceptable answer. It has the merit of not only being quite elegant and it's exact and looks mathematical. It has the advantage of G is not really universal. G varies, even on Earth. It varies between, I think on the equator it's 9.78 or 9.79, and closer to the poles it's closer to 9.9, I think 9.85 or whatever. I think physicists often use the value 9.81. We sometimes even round it to 10 in maths. Our default is G is 9.8. Okay, but so the merit, it has some merit of leaving it exact there, because whatever G is, then it actually makes the thing more precise. I think it's probably safe to actually do that and give the answer to also to the amount of significant figures that you think is appropriate. If we're taking G as 9.8, which we do in mechanics often, that's the default thing that we take, times then to two significant figures, that's going to come to 1.4 meters per second squared to two significant figures if you've used 9.8. If you've used 9.81, then it's going to come to 1.39 meters per second. Okay, so that's but anyway, that's it really. We've been through quite a bit. We've looked at a equilibrium situation. We've looked in detail at the idea of limiting equilibrium, and finally we've done a more involved situation where we've applied F equals ma and found the acceleration up the slope. And it's useful, I hope, to see the contrast between the equations that we wrote here when it was equilibrium. In fact, this one was virtually the same, apart from the sine 45. Here, the only difference was it's not zero, and we chose to go in a different direction because it was accelerating down the slope. Okay, so that's it. I hope you found this useful. It's gone on a bit, but I hope it's been in some ways useful for you. Thank you. Bye.